Yaskawa. You're watching the PLCopen Basics video tutorial series. This video shows how to accomplish electronic gearing. Hi, I'm Matt Pelletier. I'd like to give you a quick overview of electronic gearing and then get to work right away to implement an example and test it out. Electronic gearing comes from the concept of mechanical gearing, where you have two shafts turning that are mechanically coupled together through some sort of gear ratio. So this picture would show your typical input gear, which we would call the master, because it's driving the output gear or the slave gear at a certain ratio. And of course that ratio is the ratio of teeth on the gear, and could also be expressed as a ratio of units moved, maybe rotations moved on one axis versus the other. So transpose this down to electronic gearing, and you have the input master is any axis with an encoder, and then the slave, the output of the gear, is the servo axis that we are controlling. So one of the servo motors. So for example, the master could be the external encoder, it could be one of the servo axes, or it could be a virtual axis. Really, any of the axes can be a master. But the slave is always the servo axis. It's the axis that the controller is commanding in the case of electronic gearing. And now the gear ratio between slave and master is given as the number of slave units divided by the number of master units, and the required ratio of motion using those native units of the axis. And this is in accordance with PLCopen units. So we never look at the number of pulses or the number of rotations unless that is the unit set for that axis. The units for our project are found in the hardware configuration. If you click on the configuration tab for any axis, you can see the user units that have been selected here, and then the mechanical feed constants and the mechanical gear ratios that have to do with that axis motion. So we're using millimeters on the screw. The rotary is using degrees. The virtual is using millimeters, and the external is using pulses. So if we had a ratio of 1:1 with the external encoder as the master, that would be 1 pulse for every 1 millimeter of the screw if the screw was the slave. Whereas if we use the virtual, then a 1:1 ratio would be 1 millimeter for every 1 millimeter. So the units here are very important when you're going to set this ratio. Gearing in PLCopen uses the MC gear in function block and MC gear out. Gear in engages the slave to the master using the execute input. Get a master and slave axes now, 2 axes on 1 block, and the ratio as the numerator and denominator like we just talked about. And then the acceleration or deceleration rate, which applies if the master is already moving, so that the slave can accelerate to the speed or decelerate if the ratio is reduced while the slave is in motion. And then MC gear out, which you only need to give it the slave axis, tell it to execute, and it's like separating the mechanical gears from each other. And what's interesting about gear out is that when that separation occurs, the slave will continue to rotate. However, it's not linked to the master electronically anymore. So just like if you had some kind of a clutch system, you could separate the slave from the master, and the slave would not instantly stop. It may stop due to friction, but in the case of electronic gearing, it's operating as if a frictionless system, and the slave would just continue at the previous speed. So we can try out some of these things if we build an example real quick. So follow along with me like we've done before, and let's make the gear POU. So insert this program called gear. Let's put it in the medium task. Program instance, gear. And then let's open the gear POU so we can start the program. Here's my proposed program example, which is just a very simple example with gear in and gear out, and the gear out is linked to a stop. We use an R trig here so that the done output just pulses on, thereby pulsing the MC stop so that the MC stop does not keep the axis stopped, but releases it after one scan. And I also have a disable bit here so that we can take off this part of MC stop and analyze the behavior as I was talking about previously. So your programming challenge this time is not only to enter this code, but then to jog the master, which is the rotary axis, and then execute gear in under different conditions. The two conditions I'm thinking about are when the master is already moving, or to engage before the master is moving while the master is stopped, and then later jog the master. Now the thing I want you to try is adjust this ratio. Those are numerator and denominator. And what happens if you change those? When do they update? And also keep your eye on the in-gear output and see when that turns on. In-gear tells you when you're done accelerating or decelerating between the two different speeds, and you're actually synchronized, phase locked in between master and slave. These questions and a few other ones are also listed here, and I highly recommend that you use a logic analyzer just so that you can see more carefully the exact profile that the motors take, which is not always visible over the IP camera or even with the naked eye. So please refer to this page and the previous code page, and let's take some time to see what you can come up with, and then we'll review this here after the break. Okay, we're back from the break here. On this one, I'm not going to go through how to build this. I think at this point that's not an issue. All right, let's go over the gearing program and look at some of these questions. First thing to do is be sure that you can jog. And I needed to build the jog for the rotary axis. And I notice my speed is 0. And that shows me I need to do a warm start to load those initial values that I know I put in there. So my servos are enabled. Now let's jog that right-hand motor, the rotary. And the manual POU confirms that that's operating properly. So I'll close that and split my window here. And I'll give it a shot. Some of you can see that I have a mistake already. Do gear in. And you see I've got an error. It's a very common error. That's why I wanted to show it. Let's see what this error is here. 4666. Go to help. And 4666 denominator is 0. Oops. Gear denominator is 0. Can't divide by 0. That happens if you don't have an initial value. Let's start with a gear ratio of 1 and re-execute the gear in. There we go. And a 1-to-1 ratio in this case is really 1 millimeter for every 1 degree, but the way our units work out, it is also 1 rotation to 1 rotation ratio. And so this first question is, what is the difference between executing MC gear in when the master is already moving, like we just did, versus when the master is stopped? And why don't we use logic analyzer, and we'll add to that master speed, slave speed, and in gear. So I'll start with in gear is right here. Add to the logic analyzer. Let's see what we have there in the logic analyzer. I have just in gear. So we'll need to find the two speeds. And one way to do that is from the project tree. I know that the global variable for the axis can be added to the logic analyzer. And when you right click on that structure, you can choose the parameter that you want. Remember, the axis parameter struct gives us the actual velocity. So let's choose the actual velocity. Let's also do the actual velocity of the screw. Add to logic analyzer. Then under PRM, again choose actual velocity. So I'm going to remove gear in and give it gear out. And watch it stop here. Notice the master keeps jogging. I think I'll stop the master. And now we set up the trigger configuration. And let's use this in gear rising edge. It means we're triggering on that in gear output. So we'll need to see what's happening before that. Maybe 100 cycles before that. And 200 after. Let's try that. So you can hit record here, start recording, or F11. Jog the rotary. And toggle gear in. So here, let me disconnect this logic analyzer. And we see that in gear turned on. And I see one issue right away. It looks like my rotary speed is not coming up. That makes me think that we had never monitored the parameters for the rotary axis. So why don't we go check on that? And yes, that is true. We did the screw and the virtual, but I never did the rotary. Okay, so now I've implemented read axis parameters for the rotary, and I think we can turn the gear out. So now let's hit record and try that again. Recording, waiting for the rising edge. I'll hit gear in. And now in the logic analyzer. That looks a little bit better. So here we see the feedback speed of the rotary axis, and it's just showing every single fluctuation that it's experiencing here around 180 degrees, about 175 to 185 right here with the default tuning. And the actual velocity of the slave, of course, is trying to follow that. And now using left click and drag and right click and drag, you can kind of zoom in on there. But the important thing that we're looking at here is that there is an acceleration. And this is that acceleration rate that we programmed in at 360. So now for comparison, let's start the graph again. This time we'll engage the gear and then immediately jog the rotary. So engage gearing, jog rotary. And I'll stop the jog. So you see that the jog stopped immediately and the slave is still synchronized, so it stops immediately with it. Now view the logic analyzer. And it looks like I'm stuck here at 0. I didn't get quite enough time. Let's change the trigger settings here. Give it a bunch more time. Okay, so we'll remove gear in. Let's do a gear out. Be sure it's out. Now start recording. And we'll tell it gear in and jog the rotary. You can tell even visually, it just took off right away. I'll stop the rotary. And let's look at the logic analyzer. And here you can see the difference in the sequence. In gear came on ahead of time, and they both accelerated at the exact same rate at the exact same time. So the conclusion might be that if you want the axis to remain phase locked from the beginning, the easiest thing to do is leave the master stopped, execute in gear second, and then start the master after the slave or slaves are engaged to that master. Question number 2, how can the gear ratio be changed without stopping the slave? And I think that was pretty easy to show. Let's engage the gear and jog it. And then here in the gear POU, just go and change the ratio. Let's change the numerator, maybe from 1 to 4, something that's easy to see. But notice right now it's still going at the same ratio because, remember, PLCopen, rising edge of the execute input. So we'll need to toggle this gear in. We'll do that through the HMI. Just turn this off and then toggle a gear in again. And now it's running quicker and the in gear has turned on. And you could change it back to a 1 also. And we could even record this one. So recording, looking for this rising edge of the in gear input. So I'll go execute in gear again. And you see the slowdown came. See what we've caught here in the logic analyzer. So it looks like we caught the end of this decel here. So there is some transition time based on the XL and decel rate. Number 3, under what conditions does the slave disengage and no longer follow the master? One way to test this would just be stop the master and see if the slave follows it. So we can easily stop the master. We can see right now it's engaged. What if I take off the gear in input? So now the execute input is no longer running, but you know what? It says here in gear is still true, so I'd expect that it still is in gear, and that is the case. So obviously if we were to gear out, now we can see that the slave is no longer following the master. But this question 3 really leads into question 4. Disable execution of MC stop. How does this affect operation? And does the slave still remain engaged then? So we'll jog the master. We'll gear in the slave. Can release that gear in. And now in the gear code we have this disable bit, which you should be able to overwrite to a true. And that's going to prohibit the stop from executing. And you'll see now why we need the stop. Back to the HMI POU, let's gear out. And it doesn't seem like anything's happened. If you look over here at gear, however, it shows that we're not in gear anymore. So that should be a clue for you. And if we go and stop the master, you see that the slave continues. So slave's continuing at the previous speed. This is an important property of the PLCopen gear out function block, is that it does not stop the motion. Instead, it leaves the slave to run at the previous speed, but no longer following the master, obviously. Now question 5 says change the master to the virtual axis. And what are some advantages and disadvantages? So I will show that code change. It's not too difficult. We just go here to master and change it to virtual.ref and download changes. All right, close the resource, back to debug mode. I think it's probably also a good idea to add the virtual axis speed to the logic analyzer. So go add to logic analyzer. We'll take the PRM called actual velocity. I think to stop this axis, we're going to need to just go up here and stop them all and turn that back off. And now let's jog the virtual axis. And if you're not convinced, you could view that in the watch window. The virtual PRM actual velocity right now is a perfect 180. Let's record this one before I do it. Down to gear in here, let's turn that on. You can see now we're gearing to the virtual, just like we were to the real axis. We can change that ratio just like on the real axis. So overwrite it to a 4 and then re-execute the gear in. And now it's going fast again. And we can stop jogging the virtual. And it stops. We can go the other way. Takes off the other way. And let's take a look at the logic analyzer. If you really want to see what the servos are doing, the way to look at it is with SigmaWin Plus over USB connection. But discussing some of the advantages and disadvantages, there's a lot of advantages to using the virtual axis. Number one, of course, is that if all you need is a master, you can use the virtual axis, and you don't have to buy an axis to run anything else. So the virtual axis really acts like an internal clock, and you can then use your real axes to slave off of the virtual as the master. And one advantage that has is just in performance, axes are automatically synchronized to each other. I think the only disadvantage, the virtual axis does not behave exactly the same as the real axis, so there may be some coding differences. And of course you can't really see the virtual axis, so that could be a disadvantage also. But there's definitely a place for the virtual axis, and performance is generally increased when all of the slaves are gearing off of the virtual axis versus using one of the real axes as a gear. The final page of this section is just a reference here for you to look at the master when it's stopped and geared in versus the master already running and you gear in with that slower acceleration rate. So this is the end for this section. So it's time for us to wrap it up and do a final save as and zip it here to project 12 gearing. Thank you. That concludes this video.